Welcome to this lecture series in linear algebra. In this lecture, we'll look at the notion of the span of a subset of a vector space. And let us recall what we have done so far. So we have discussed what are fields and vector spaces. And last time we discussed the notion of a subspace. So if we are given a subset of a vector space V, we call it a subspace if it is closed under addition and closed under multiplication. Well, by multiplication, I mean scaling. So such a thing is called a subspace, and we discussed this at length. But one of the properties that we saw was that if we intersect any collection of subspaces of a vector space, then we again get a subspace. Right? So this will be one of the main things that we will need for this lecture. All right. Here are some problems for practice. And now let us get started. So fix a vector space over some base field that is not important, over some field F. Okay, and suppose we have a non-empty subset of the vector space. Then we define the span of A as the intersection, not the intersection, we'll come to that, defined as the smallest subspace of V that contains A. So it is an informal statement as of now because what one means by smallest is unclear. Subspaces are not numbers that one can compare. So we will make this precise as follows. So span of A, we want to define span of A. So let the script S be the collection of all subspaces of V which contain A, which contain the set A. Then span A is defined as the intersection of all the things in script S. So in this sense, it is the smallest subspace that contains A. If you have any other subspace that contains A, span A will be contained in it immediately by this definition. And span A is a subspace because intersection of a collection of subspaces is a subspace. So this is a very nice definition. All right, I hope this is clear. And here is a simple remark which you can take as an exercise, that if we have A contained in B, then span A is contained in span B. Okay. So let's look at two examples. We have R2 and we have a point in R2, and let's say A is this point. So the singleton is the set A. What is the span of A? First of all, it should be a subspace and it should contain A. So subspace containing this point, well, recall that the subspaces of R2 are precisely the lines passing through the origin, the entire R2, and the trivial subspace. So it has to, whatever is the span of this point has to contain this line, because it has to be a line passing through the origin which passes through this. And this is a subspace already. And therefore this is going to be the span of A. So I haven't given a formal proof, but you can argue that the span of A is nothing but the line passing through this point and the origin. What about 2 points? We have 2 points not lying on the same line passing through the origin. What is the span of these two? The span of these two is everything, the entire R2. And I leave you to figure that out for yourself. All right. Now we come to another very important notion called linear combination. So fix a vector space over some field F, and suppose we have chosen some bunch of vectors from the vector space. Then a linear combination of the chosen ones is defined as anything in V of the form, or rather, how should I express it? Any expression of the form rather, of the form alpha 1 V1 plus dot 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 alpha n Vn, where these are from the base field. So such an expression is called a linear combination. Of course, this is a vector in V because all of these are vectors in the space V and we have just summed them. This is a vector in V, but we are not just calling the vector as a linear combination. This particular expression is what we are calling as the linear combination. Sometimes we do not make a distinction, but as of now, we will. All right. The very simple definition, and here is a simple remark. Any subspace is closed under linear combination. What does that mean? It means that suppose we have a subspace of a vector space V and we choose some finitely many points in S and take a linear combination of our liking. That linear combination will lie in S. That's what this means, and that's a trivial statement, but I just wanted to delineate it. Okay. Now, using the notion of linear combination, we can give a descriptive definition or a description to the notion of span. We define the span of a subset in a rather abstract way, in a beautiful way, but in a rather abstract way. The theorem that we have written here, or lemma, whatever you want to call it, is giving us an alternate but a more hands-on way of looking at what is the span of a subset. So fix a vector space fix a vector space over a field F, A be a non-empty subset. Then span A, as we have already defined, is the intersection of all the subspaces of V which contain A, can also be described as follows. Take any finitely many elements in A and take a linear combination. Just collect all the, basically it's all those vectors in V which can be expressed by taking a linear combination of some finitely many vectors in A. That's what this is. Okay? So in a more somewhat traditional manner, or more, I don't know what to call it, another way to express the same set is as follows. Alpha 1 V1 plus dot 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 alpha n Vn, where n is any positive integer and each alpha I is in the base field and each Vi is in A. So I should say for all I. So this and that are the same things. Okay, so let's prove this. So first of all, maybe let us call this thing U. Let me call this U. So first check that U is a subspace. Note that U is a subspace. Very easy to check. Just check it is closed under addition and scalings. Also, U contains A. Right? Because if you have a vector in A, you just consider this linear combination 1 dot V. So definitely this subspace contains A. And therefore, since span A is the smallest subspace containing A, we have span A is contained in U. So we need to do the reverse containment. Okay? But at the same time, since subspaces are closed under taking linear combinations, any subspace that contains A will contain U. So any subspace that contains A also contains U. Again, because subspaces are closed under taking linear combinations. And therefore, since span A is a subspace that contains A, we have the reverse containment already. And that's the proof. So if you just take these two containments into account, we get this equality. Very simple. Okay. Now for the notion of a spanning set. Fix a vector space over some field F. A subset A of V is called a spanning set if span of it is everything. Okay, nice definition. We will look at examples, but before that, we say that a vector space V is finitely generated if it has a finite spanning set. Okay? So two definitions, and we will fortify our understanding using examples. So Rn. Let us first write down a spanning set of it and then make some further comments. So define E1 as this element, E2 as this element, and so on up to En as that. And let A be this set. So pictorially, in R2, all we are doing is, So in R2, this is E1 and that is the E2. Okay. And in R3, you can draw your own picture. So note that span A is everything. Why is that? Because what is alpha 1 V1, alpha 1 E1? The reason is very simple. The reason is that alpha 1 E1 plus dot 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 alpha n En is nothing but this particular tuple, which shows that anything in Rn can be written as a suitable linear combination. And you do not need to think too much basically here. It's just immediate. So clearly span A is Rn, and we have found not just a spanning set, but a finite spanning set. So this shows that Rn is finitely generated. Okay. And similarly, you can show that Cn and Qn and all of these things, in fact, you can show that Fn is finitely generated, and also, Rnx, Qnx, Cnx, and in fact, in general, Fnx, F is any field. These are all finitely generated, and this thing is finitely generated if X is finite.